All right, now that we've looked at improper integrals, now let's look at convergent and divergent. So if our limit exists here, we're going to be getting a convergent. There's supposed to be a dx on there. And then if it doesn't exist, we're going to be getting a divergent. So let's take a look at two examples to see why that is. So this would be the limit as t approaches infinity of the integral from e to t. So again, all we're doing is replacing the infinity with a t. 1 over x ln of x squared dx. And so now we can take and find out what our integral is. So 1 over x ln of x squared dx. And you could see that we do have an ln of x here. And if we take the derivative ln of x, we're going to get 1 over x. So that is the u that we want to use. So du is equal to 1 over x dx. So we can then take and substitute that for our du. So we end up with the integral of 1 over u squared du. And then this is integral of u to the negative 2 du. And again, we add 1, so we get negative 1 over u. Oops, no more integral. Just like that. And then we plug it back in, so negative 1 over ln of x. And so if we added 1 to this, we would get negative 1. Flipping it then is 1 over u, and with a negative, so we have negative 1 over ln of x. So now we can come back and actually finish this. So this is the limit as t approaches infinity of e to the t. Oops, we don't need that anymore. It's negative 1 over ln of x, t, and e. So all we're doing is putting it back. So we've already taken the integral now, and now we're making it a definite integral. So we're not putting plus c on it. So we're putting our t and e in, and then now we just plug them in. Positive, that's an arrow, that's why it looks weird. There we go. Arrow, infinity, infinity, and it's just negative 1 over ln of t plus 1 over ln of e. All right, so this is going to equal, this is going to be a negative 1 over infinity. So again, that means that goes to 0. Plus, and ln of e is 1. So ln of e is 1, so it's 1 over 1, so it's 1. So the answer is 1. All right, and looking at Desmos, you can see as we go off to infinity, it's getting closer and closer to 1. So since we have a limit, this is convergent. It converged. All right, now let's look at one that is divergent. So let's rewrite it first. So we know this one's the limit's not going to exist. So this is the limit as t approaches negative infinity from t to 0. There we go. All right, now let's take our integral. So we have 1 over 3 minus 4x dx. And so this is a natural log one. U equals 3 minus 4x. So du equals negative 4 dx. So dx equals du over negative 4. And now we plug it in. So we end up with negative 1/4, 1 over u du. This is negative 1/4 ln of u. So negative 1/4 ln of 3 minus 4x. All right, so our integral is this, and now we can make it into our definite. So limit as t approaches negative infinity. I'm going to put the negative 1/4 on the outside, just like before. From 0 to t, and now we plug that in. So ln of 3 minus 4t minus, oops, that should be 0. 0 goes first. Minus 3 minus, with the ln, see I messed myself up there. So 3 minus 4t, and there we go. So it does double check it because I just did a horrible job there. Plugged in the 0, perfect. Plugged in the t, perfect. All right. Now, this is 3 minus 4, or 0, which would just be ln of 3. And now with our natural log, so if you remember our limits with our natural log, right? We want to look and see if it's going off to infinity or negative infinity. Those are the two things that we get when we're dealing with our natural log, our two rules. Otherwise, we have some number in between. So we know that the limit, as I'm going to make it an x, goes to infinity of ln of x. This is equal to infinity. So if I distribute this negative 1/4, I'm going to get negative 1/4 ln of 3, because we're done with the limit on the ln. And then we would get negative times a negative, so positive 1/4 limit as t approaches negative infinity, because we're not done with the t over here yet. All right, and then we can think about it. We need it to look like this. So with this function, it's negative. So if I were to do a negative infinity in there, the negative 4 would turn it into a positive infinity. So this becomes 1/4 limit, and let's just call it s. S approaches positive infinity, ln of s, just like that. Since we're approaching positive infinity, we could pretty much just throw away the absolute value, but we're going to leave it. And so now we know that that goes off to infinity. So we get negative 1/4 ln of 3 plus infinity. So this is just positive infinity, because that's not going to make a difference there, which means it diverges. The limit does not exist. Let's try that again. Diverges. So if our limit exists, we get something that converges. It's convergent. And if our limit does not exist, then we know it is divergent. It diverges. You can use either one, convergent or converges, your choice. In fact, let's change it to converges so that we have it there. Converges, diverges, and there we go. So we got one, it converged. Infinity, it diverged. And in the next video, we're going to talk about a way to look at fractions and determine if that fraction is going to diverge or converge right off the top, because it'd be nice to know, right? So we would know right off the bat that this fraction will diverge because there's something going on with it.